Good day! In the previous lecture we discussed simple hypothesis tests. Today we are going to look at the composite hypothesis tests. Remember our abstract formulation of the hypothesis testing problem where we are given a family of potential distributions for the data that is parameterized by a vector theta that lives in a certain parameter space. The goal is to determine whether the theta corresponding to the distribution in this family that generated the data that we are seeing is in the set theta 0 or in the set theta 1. Remember that these two sets partition the parameter space, which means that each theta is in one and only one of these sets. We defined a simple hypothesis test as a test where both these sets contain one element. And we said that a hypothesis test is composite otherwise. So at least one of these two sets contains more than one element, and therefore at least one of these hypotheses does not completely specify the distribution of the data. To quantify performance of the decision rules, we defined two types of errors. We say that an error of type 1 takes place when we decide H1 but H0 is true. And this is also called as a false alarm. The other type of error that we defined is a type 2 error, which occurs when we decide H0 but H1 is true. This is also called a misdetection. We use these definitions to introduce two performance metrics. One was the probability of false alarm and the other the probability of misdetection, which is the complement of the probability of detection. And we presented the Neyman-Pearson theorem, which provides the test that maximizes the probability of detection among all tests with a given probability of false alarm. But here it is crucial to note that this theorem applies only for simple hypothesis tests. However, in practice, most of the tests that we will encounter will typically be composite, right? And this essentially means that the distribution of X under at least one of the hypotheses contains unknown parameters, which are sometimes called nuisance parameters. And there is another ingredient that complicates composite hypothesis tests, and it is the fact that the probability of false alarm and probability of detection will in general depend on those unknown parameters. As an example, we can extend one of the hypothesis tests from previous lectures. Suppose that under H0 the data contains only noise. This noise will be modeled as white and Gaussian, which is of course a very common assumption. And under H1 the data contains both a DC level component and noise. So unlike in previous lectures, here A is unknown. And of course, it must be different from 0, otherwise both hypotheses would conflict. And it is crucial to become familiar with different ways of expressing the same hypothesis test. An obvious one is just or follows by collecting these samples here to form vectors, as we have extensively done throughout the course. One can also recognize that the equation provided by H0 is a special case of the equation provided by H1 when A equals 0. So this means that we can define x by the same equation under both hypotheses, and then we can formulate the hypothesis test in terms of the value of these parameters. So this is also a common way to write this kind of problems. But instead of specifying an equation, we can provide the distribution of the data under both hypotheses. Here we see that we only have one distribution here, whereas here we have one distribution for each possible value of A. And in a totally equivalent form, this can be phrased as X has a distribution P, and under H0 P is in this set, whereas under H1 P is in this other set. So from this we see that we can now express the problem in the canonical form of the previous slide. If we just state that X has a distribution P theta given by a Gaussian distribution with these parameters, and under hypothesis H0 theta is in this set theta 0 that contains only the 0, whereas under hypothesis H1 theta is in this other set theta 1. With this notation, it is crystal clear that this hypothesis test is composite, right? Because this set contains more than one element. And this slide therefore shows why saying that a hypothesis test is composite when one of these two sets contains more than one element is equivalent to saying that there are unknown parameters under at least one of the hypotheses. Now that we are familiar with composite hypothesis tests, the next step is to design decision rules. Remember that when we dealt with simple hypothesis tests, we adopted the probability of false alarm and detection as our performance metrics, but we observed that there was a trade-off between them. And that led us to introduce the famous Neyman-Pearson criterion, where we maximize the probability of detection subject to a bound on the probability of false alarm. For composite hypothesis tests, now we will have to generalize those ideas. And to that end, let us first note that when a hypothesis test is simple, we can adopt this kind of notation. That is, we can specify the PDF for the data just by indicating the hypothesis, right? There's no ambiguity there. And similarly, we can use this notation to refer to the probability measure under hypothesis H0, but also for hypothesis H1. However, this is not something that we can do for composite hypothesis tests, because the distribution of x depends on this on theta, even within each hypothesis. And as a consequence, since the decision rules and test statistics are functions of the data, their distribution will also depend on theta. So the implication is that the probability of false alarm will also be a function of theta, and it will be defined for those thetas in the set theta 0. So note that this will be this is the definition, where here this is the probability measure that we need to use. One can, of course, condense all these numbers here into a single one, which can be, which is typically the worst case PFA, right? Which is the supremum of this probability of false alarms across the values of theta in theta 0. Similarly, the probability of detection can be written in this way. So the expression is the same, right? But now theta is in the set capital theta 1. And with these observations, we can now extend the Neyman-Pearson criterion to composite hypothesis testing. And to that end, we will use the following definition. We say that a test or decision rule, classifier, and detector, right, is uniformly most powerful with size alpha if two conditions hold. The first one is that the probability of false alarm is less than or equal to alpha. Okay, this, remember, that was called also the significance level. And this must hold for all values of theta in theta 0, right? So an equivalent condition would be requiring this worst case PFA to be less than or equal to alpha. And the other condition states that if there is another test, d prime, whose probability of false alarm is less than alpha, then its probability of detection cannot be greater than the probability of detection of the uniformly most powerful test, right? And again, this should hold for all theta in theta 1. This is precisely what gives rise to this name, why we call it uniformly, okay? So, in a few words, D is uniformly most powerful with size alpha if its size is alpha and it is more powerful than any other test with size alpha. So this definition looks beautiful, but I have bad news for you. It turns out that the uniformly most powerful test does not necessarily exist. And this is precisely because of this condition, which is too strong, right? The same occurred when we looked at minimum variance unbiased estimators. We also had universal quantifier there, and that was the problem, right? It was not possible to minimize variance for all possible values of the parameter. But let us not start crying. Let us see how we can try to come up with a satisfactory decision rule. To that end, let us start by recalling what we did in the case of simple hypothesis tests. There, the Niemann-Pearson provided the most powerful test, whose test statistic was the so-called likelihood ratio. So there we divided the PDF evaluated at the data under both hypotheses and took the quotient. However, now we couldn't follow such a procedure because we don't know these parameters here, right? There are more than one possible value of the parameters, at least under one of the hypotheses, and therefore these functions wouldn't be this would depend on the true parameter, and therefore we wouldn't be able to evaluate the corresponding test statistic, right? Because if we knew the parameter, then we would already know what hypothesis is true. But what we can do is, instead of using here the actual parameters, we can plug estimates of them, right? And in this context, the most common approach is to use their maximum likelihood estimators. So this brings us to the so-called generalized likelihood ratio test, which is given by this expression here. So the test statistic is looks like the test statistic of the most powerful test for a simple hypothesis test, but these parameters are replaced with their maximum likelihood estimators. So remember that the maximum likelihood estimate is the value of the parameter that maximizes the likelihood function, which has the same functional form as the PDF, and therefore this can be written in this way. So this is a sort of taking the value, or taking the PDF that explains best the data and compare them under both hypotheses. The threshold is again adjusted to attain a desired probability of false alarm, but here there's a subtlety. As we said earlier, the probability of false alarm depends on theta, so we need a way to make up our minds and decide for which value of theta we want to set the corresponding threshold, or perhaps we can look at the worst case probability of false alarm as defined earlier. This test is not generally uniformly most powerful. However, it typically has a good performance, and furthermore, it is typically intuitive. Okay, so it agrees with this notion of best guess that we developed earlier in the course. So let us illustrate this by revisiting the example of DC level estimation in white Gaussian noise. The test statistic of the GLRT is, by what we saw in the previous slide, given by this expression. So now one just needs to substitute the expression for the PDF associated with this distribution, both in the numerator and denominator. And to solve these optimization problems, it is useful to note a couple of facts. One of them is that the supremum of a function over this set equals the supremum of that function over this set. And this is a consequence of the fact that the supremum of a set equals the supremum of the closure of that set. And if you are not familiar with that, it's not really important to follow the rest of the lecture, but of course it is also intuitive. And the second fact is that we have already maximized this function earlier in this course. This was when we were doing a maximum likelihood estimation, where we found that the theta maximizing this likelihood function is precisely the sample mean of the entries of X. Okay. So with these observations in mind, one can just find this supremum, right, which will be the result of substituting this X bar here. The supremum in the denominator is much easier because there's only one possible value allowed for theta, and therefore we just replace this theta with a 0. And cancelling these coefficients just yields this expression. Now one can combine these exponentials to write the test statistic in this way, and this can be further simplified. First, we can cancel these two terms. Second, we can note that the square norm of the vector of all ones is n, right? Because this is the size of this vector. And third, note that X transpose 1 is the sum of the entries of X, and therefore this is equal to n times the sample mean. So this yields this expression here. And as we did in the previous lecture, it is often convenient to obtain a simpler expression for our test statistics. So in this case, we can do so by noting that this inequality here is equivalent to this one, right? So we just need to take logs on both sides and multiply by 2 sigma squared divided by n. And now one can just note that this inequality holds if and only if this inequality holds, right? So it is important to remember that we need an absolute value here, because every number has two square roots, right? A positive and a negative square root. So let us denote this coefficient by gamma tilde, and with that we can write the GLRT in this way here. So we just need to compare the absolute value of the sample mean with a threshold to make a decision. Note how intuitive this test is, right? So think that if somebody asks us if the mean of a signal is 0 or not, it is very reasonable to estimate the mean of that signal and then see if it is far away from 0 or not, right? So let us now briefly discuss how to apply the concept of ROC that we studied in the previous lecture in the case of composite hypothesis test. Remember that for a simple hypothesis test, the PD and PFA are functions of gamma. And therefore, for every value of this threshold, we obtain a pair of points. We said that receiver operating characteristic, or ROC, is the set of all these pairs of points, right? And this could be represented pictorially like this. We said that there were two important benchmarks. The upper benchmark is the most powerful test, right? So all other tests need to be below the ROC of the most powerful test. And then there was a lower benchmark which was given by the oblivious detector. This is a detector that just disregards the data and essentially tosses a coin, right? So every reasonable detector must be somewhere in between these two curves. In the case of composite tests, the PFA and PD not only depend on the threshold, but they also depend on the parameter of the distribution. So specifically on the nuisance parameters, right? So this means that for each pair, theta 0, theta 1, we will have an ROC, a curve, right? And therefore it is very important to indicate what values of theta 0 and theta 1 we are using, right? So one can see sometimes in papers of poor quality that they don't completely specify the ROCs that they are plotting. So, but instead of just perhaps providing a bunch of ROCs, each one for a different pair of parameters, one can use other alternatives. So one could, for instance, average and the PFA or PD using a certain distribution of theta, right? This would be sort of halfway between Bayesian and non-Bayesian. But this could be done, for instance, with Monte Carlo, right? But there are other possibilities to condense the information in these ROCs into perhaps a single curve. So to conclude, let us recap the main messages here. We said that the Neyman-Pearson theorem provides the most powerful test for a simple hypothesis testing problem, right? However, most of the hypothesis tests that we encounter in practice are composite, which means that there are unknown parameters, right? And this implies that the probability of false alarm and probability of detection will depend on those unknown parameters. And as a consequence, one cannot talk about most powerful tests. What we had to do is to extend the notion of most powerful test to accommodate this dependence, and that brought us to the definition of uniformly most powerful tests. We said that those tests are the ones that maximize the power among all tests with a given size, but for all values of the parameter, right, under hypothesis H1. Unfortunately, UMP tests do not exist in general, also, although sometimes they do, of course. To remedy this issue, we introduced the so-called generalized likelihood ratio test, which is inspired by the most powerful test, right? The difference is that in the most powerful test we use the likelihood ratio, and here we use the generalized likelihood ratio as our statistic, which coincides with the likelihood ratio upon replacing the unknown parameters with their maximum likelihood estimates. The GLRT is not necessarily uniformly most powerful, but it typically has a good performance, and besides it yields intuitive decision rules in many cases. So what remains is to accommodate prior information on what hypothesis is true, right? This will bring us to the notion of Bayesian detectors, right? And we will explore that briefly in the next lecture. And one could also think of hypothesis tests with more than two hypotheses. Unfortunately, we don't have time in this course to cover it, but it can be found on books. Now you have a solid background to understand those sources. So this is all for today. Thank you for your attention.